I hear some voices. There are people here. There. All right, folks, well, welcome back. Any problems logging in or anything? They did tell me over the weekend that they were going to start increasing the security of the Zoom that we're using at UT. It's supposed to start to involve passwords, I think. I don't know exactly what they're going to do. As far as I can tell, you don't need a password to log in as long as you use the utexas.zoom.us interface to start logging in. All right, well, anything you need to ask me about the material that we've been working on or the homework problems that you've tried or anything like that?
I have a question about like the extra credit for the recent homework.
Oh, yeah.
Like question A, like how much calculator usage are we supposed to or like I have to use some of the I have to use calculators to solve some of it. But are we supposed to be able to do it completely by hand or?
No, I don't mind now if you guys are using calculators. In fact, you can get much more interesting examples if you're starting to use a machine. So go ahead and use a calculator or even a computer to start generating some sort of more complicated examples. I've been trying to give you some that you could do by hand, but I do know that for some of them at least, like the very simple task of taking an integer and reducing it modulo n. I mean, I'm going to do some examples today with n being a number like 143. And if the number you're trying to reduce mod 143 has got 5 or 6 digits, you'd have to like manually divide 143 into the big number and carry it out until you get the remainder.
Are you leaving like fast modular experimentation or that type of?
Yeah, well, there again, if you're only working modulo a smallish number, you can keep reducing modulo that number, and that way you won't exceed the capacity of a calculator. So go ahead and, like, if I wanted you to erase a big number, in fact, I'm going to do that today, raise some big numbers to maybe even a very big exponent, but to do so modulo 143, yes, you would just do a number of squarings and small multiplications, but you would never have to be dealing with anything more than like a 6-digit number, which you would do on a calculator. You don't need a computer. You would do with a calculator. You can manually on the calculator just divide by 143. That tells you when you round down, then that gives you the quotient, the Q that shows up in the division algorithm. And when you subtract something minus Q times 143, then that'll give you your remainder, your reduction mod 143. So yeah, it takes a few keystrokes if you're just entering each number by hand into a calculator, but I'm trying to make it so that it's not too much work. Let's put it this way. I think on the last homework, I did test the calculations I was having you do to see if I could just do them by hand in a few minutes rather than, I mean, by hand meaning with a calculator, but not using a computer. I have my computer rigged up to handle some of the larger calculations for me very fast, little subroutines that we do very often. But I know you guys don't have that, so. Was there a calculation that looked like it was taking forever with a calculator that you want to ask me about?
Oh, nothing that was taking forever with the calculator. It was taking forever for me to do by hand.
Oh, yeah. Nah, you don't have to do it by hand anyway. In fact, this is like one silver lining to this whole coronavirus thing is now that we're all apart, and I don't really have any way to give you guys an exam that would be proctored, I would ordinarily on an exam, I would say, yeah, no calculators, no phones, no nothing. And now I can't assume that you guys would stay away from those things. So now I can write an exam that says, yeah, go ahead, use a calculator. And then you can start to have some more interesting problems. So yeah, calculators for sure.
Thank you.
They're fun. Yeah. I still don't want you using a phone in the sense of I don't want you phoning a friend. And yeah. But anyway, we'll come to that when we get to the exam. All right. But I do want to start doing some more stuff with the Euler Phi function, and we'll see some of these consequences. I'm actually getting kind of impatient. I want to start showing you guys the encryption algorithms that are built on some of these things. So yes, I do want to do some calculations that they won't really make a good encryption routine if you're doing them on a calculator, just on your phone. But the principles are the same. If you do them on a computer, it's just the computer can handle much bigger numbers. And then you really do have something that's, we think, pretty secure. All right, let me swing my camera around and start writing some stuff out for you. Okay. So, yeah, we've been talking about this Euler Phi function. And I guess this is the definition that I ended up giving you, that phi of n for a positive integer n is just going to be n times the product over all prime divisors of n of 1 minus 1 over p. And this is a very strange looking formula. There would be no real reason for a person to invent it if it weren't for the fact that we get Euler's theorem out of this. So Euler's theorem says that if a is any other integer that's coprime to n, then a to the phi of n power is congruent to 1 modulo n. So this, I'm going to be doing some things with this today, trying to take advantage of that for some numerical calculations. But I got a few other things that I want to talk to you about before we get into this. So the first is this. There's another interpretation of what phi of n measures. And this interpretation at least makes something clear that if I had just written out that formula, it would be a head scratcher. You'd have to think for a minute to convince yourself that this really is an integer. It doesn't take long, but you do decide that it's an integer. Positive integer. It's a positive integer that's less than n. I said all that last time. But there's actually a good reason for this to be a positive integer that's actually smaller than capital N. Because when somebody defines an integer for you, rather than just having a means to compute it, you might ask, what does this integer count? What does this integer stand for? And that's this theorem. Phi of n is the cardinality of a set that we've already encountered. I'd like to first write this set, but this is wrong. Just so you remember though, what is this z sub n? You know the z is the set of integers, and with the sub n there, you remember that that stands for the set of congruence classes of integers modulo n. So we took all the integers and we partitioned them into, well, it was a grand total of n separate categories, n equivalence classes. All the numbers that are equivalent, that are congruent to each other, you put them into a certain lump. And so then we ended up writing the set of all integers as, well, there's all the integers that are congruent to 0 mod n, together with all the integers that are congruent to 1 mod n, and so on. So the set of different congruence classes, these items together, that's the collection of these things is Zn. I don't know how to write that in symbols. I think the words say it better. Anyway, it's obvious that the cardinality of that set is n. There are exactly n congruence classes modulo n. Every integer is congruent to exactly one of the integers from 0 to n, well, 0 to n minus 1 inclusive. So what's phi of n then? It's not n. It's something less than n. It's the cardinality of a certain subset of z mod n. Specifically, what this little x is doing up there as a exponent is it's not an x, that's the multiplication symbol. That's times. And that's because this notation stands here for the set of things that you can multiply and have inverses. So this is the set of invertible congruence classes modulo n. Just for an example here, when we look at Z mod 12, well, that's a total of 12 congruence classes. And if you permit me to not write all the symbols, I'll just call them 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So there's all 10 of the congruence classes. Now, which ones of them have inverses modulo 12? Well, nothing that's even will have an inverse mod 12 because 2 is a divisor of 12. So all of this half of them has to be crossed out. Moreover, 12 is also a multiple of 3, so any congruence class that is a multiple of 3 also has to be excluded. So all you have left are the congruence classes of 1, 5, 7, and 11. And each one of these really is invertible. In fact, as it turns out, in this particular case, every one of these is its own inverse. 5 squared, 25 is congruent to 1 mod 12, 49 is congruent to 1, and 121 is congruent to 1 as well. So in this case, if I ask you how many elements there are, the answer is 4. And on the other hand, if you check, phi of 12 could be computed from the definition that I gave earlier as 12 times, well, 2 was one of the prime factors and 3 is the other prime factor. A half times 2/3 is 1/3, and 12 times 1/3 is indeed it's equal to 4. Well, it turns out that the calculation that I did is not just a fluke. Exactly the calculation that I just did illustrates why this theorem is true. So in fact, let's have a proof. This is, if you took a probability class, you had to do some elementary probability of with a finite sample space, and all of the conclusions that you get in that part of the course are based on that inclusion-exclusion principle. So here's what I mean by that. We already know that Z bracket n has a total of n elements. Now, if P is a divisor, then I know that there are some elements of Z mod n that will not have inverses precisely because they are congruent to 0 modulo P. You can't have an inverse modulo n if you don't even have an inverse modulo P, and such an element, when reduced mod P, would give you a 0. So let's say it this way, then if P divides A, then that means A has no inverse. Well, I should say it this way. The congruence class of A modulo n has no inverse in Z mod n. So the number of elements that are in Z mod n is already got to be smaller than n. Cardinality of the set has got to be smaller than n. In fact, it's got to be at most, well, you had n elements in the first place, but all the multiples of P within the numbers from 1 to n, all of those multiples of P have to be excluded because they will not have inverses. So we have to subtract off 1/p of all the elements of n. This is precisely the number of multiples of P that there are. The numbers A that have this condition are the numbers A times K, where K starts at 0, and you have to stop when you get to K times A being greater than n. In other words, when K is bigger than n over P. I say less than or equal to because we have to worry about other prime divisors as well, but in terms of deciding whether something has no inverse because it has a common factor with n. Well, if you have any common factor with n, then in particular you'll have a prime factor in common with n. And for any particular prime p, the things that have to be excluded because they share that particular prime factor, this is exactly how many there are. And you saw me do that up in this case where I listed all the 12 elements of Z mod 12. The number of elements that I had to exclude because they were multiples of 2 are exactly, I had to throw away 6 elements because they were multiples of 2. And so I only had 12 minus 6, which was 6, left. But now, if you have a different prime p, a different prime than p, then when I go to count the elements in Z mod n that have inverses, well, I have to exclude all the elements that are multiples of p. I've already done that. And I also have to exclude all the elements that are multiples of q. But this isn't quite the right thing to say if I'm only looking at the elements that are a multiple of p or q, because I should talk about the elements that are multiples of p or q or both. And that situation arose in here when I looked at the second prime divisor of 12. When I started crossing out all the multiples of 3, well, there were exactly 4 multiples of 3. Oops, I should have crossed this one out here as well. There were 4 multiples of 3 in the same sense that I had done over in this formula. But I've subtracted off the numbers 0 and 6 twice. I crossed them out twice, and so that was actually an undercount now. Really what I should talk about is exactly the subtraction that I have here, but I have to add back in exactly all of those candidates that were multiples of p and q. Well, if you're a multiple of p and a multiple of q, then you're a multiple of p times q because p and q are relatively prime, but they're distinct primes. So of course, this is the method of inclusion exclusion that you remember if you've done one of those counting classes, a probability class, or even just a finite math class. And it's at this point that you realize that actually these formulas can be rewritten. This one can be written as 1 minus 1 over p, n times that. And this one is now n times 1 minus 1 over p times 1 minus 1 over q. And in fact, exactly what I've calculated here is, and by either of these formulas, actually they're algebraically the same. What both of them are counting is these are the elements of Z mod n that are coprime to both p and q. You take all of the sets, throw away the ones that have a multiple of p, throw away the ones that are a multiple of q, and then add back in the ones that are multiples of both. In the same way, using inclusion, exclusion multiple times, more generally, a congruence class A, well, an integer A is coprime to a whole sequence of prime numbers. For exactly this many elements of Z mod n, n times 1 minus 1 over p1 times 1 minus 1 over p2 times, and so on, 1 minus 1 over pk. This is the exact count of elements of Z mod n that share no factors with any of these primes, that they are not divisible by any of these primes. And then finally, all you need to observe is, since a congruence class in n, in Z mod n, has an inverse if and only if the number A is coprime to n. That's a theorem that we discussed earlier. We use the fact that the GCD of A and n is equal to 1. That used Bézout's theorem. I don't know if you remember. But if A and n, if the GCD of A and n is 1, then you can find an inverse. And if the GCD is not 1, then you can't. Furthermore, thanks to the fundamental theorem of algebra, of arithmetic, these two numbers are co-prime if and only if A is not divisible by any prime that divides n. The conclusion, therefore, is that the elements that are in Z mod n cross, the invertible elements of Z mod n cross, the number of them is exactly the n times the product over all prime divisors of n of 1 minus 1 over p. And that's the formula that I gave you for the Euler Phi function. So the Euler Phi function is actually counting something. That's a very useful observation. When somebody points out that something that you've computed is going to be an integer, a positive integer, then it's a really natural question for a mathematician to ask is, what is it counting? And there can be more than one answer. And sometimes there's no apparent answer, but that's where mathematicians start doing some research. If you know you're going to get an integer for something, then they want to find a way to count, to find something to count so that they know how to compute this thing in some other way. Now, the next theorem that I'm going to give you is exactly the same as the theorem that we've had before, but it puts a whole different spin on the theorem. So if you take the result that I just gave you and you combine it with Euler's theorem, then what you get is the following result. If A is an element of Z mod n cross, so you can think of this as a congruence class of integers, or maybe just a single integer from 1 up to n. But anyway, it's supposed to be an invertible element mod n, so an integer n that's co-prime to n. Then what you discover is that if you take such an element and you raise it to the cardinality of Z mod n cross, then what you get is the congruence class of 1, which is the identity element it's the identity element of what we call the group Z mod n cross. We already know that the invertible elements can be multiplied to get more invertible elements. In fact, you know the inverse of a product is the product of the two inverses. So the collection of invertible congruence classes forms what we call a group. When you take your abstract algebra class and study group theory, this is one of the early examples that you find in a group. A group is any set on which you have a binary operation. That means a way of combining any two of them to get a third. And it has to have an identity element, which in our case is the congruence class of 1. But what Euler's theorem is saying is that the group of invertible elements mod n has the feature that if you take any element of it and you raise it to a power which is the cardinality of that group, then what you will get will be the identity element of that group. That turns out to be a really useful theorem. This is actually a theorem in group theory, so this is outside the scope of our course, but I'll whisper it to you now. This is known as Lagrange's theorem. And it says that if you take any finite group, and then you take any element of that group, you have, if you raise the element of the group to that exponent, what you will get will be the identity element of the group. So I'll put this in a circle because it's not really a number theory result anymore, but this is a result that you would use in Math 343K or Math 373K. If you haven't had those courses yet, remember me when you go to take it and the teacher mentions Lagrange's theorem. So for for sort of a historical perspective, what you should view is that this has been a three-stage process. It starts off with Fermat, who handles the case of looking at Z mod P, a very specific group. I mean, you could take any prime P, but if you look at any congruence class in Z mod P, he raised it to the Pth power and made an observation. We looked at the possibility of taking a non-zero element in Z mod P, and then we noticed that you could raise that element to the P minus 1 power to get 1 mod P. Okay, so Fermat didn't know it, but he was proving a theorem about this particular kind of group when the P in question is prime. That became a special corollary of Euler's theorem. Euler proved what amounts to the exact same theorem, but proving it for the group of invertible congruence classes modulo any n, whether n is prime or not. So Fermat's theorem, in retrospect, could be seen just as a corollary of Euler's theorem. And now what I'm telling you is that actually Euler's theorem is completely contained in, I mean, it's an immediate consequence of Lagrange's theorem. Lagrange's theorem applies to any finite group G. So that's, again, that's outside the scope of this course, but hey, I'm trying to make you guys interested in math in general and not just number theory. All right, so that's the first thing I wanted to give you today was an insight as to, well, A, what does the Euler Phi function actually count for you? And B, how does it fit into a larger context? Let me show you another theorem, which now there's actually two proofs that I could give you. One is kind of boring, and one now is kind of interesting, I think. So here's the theorem. It says that if you take two coprime integers, A and B, and you want to compute the Euler Phi function of the product, that's the product of the two Euler Phi functions. You can give a proof that's not too complicated by just using the definition of how I define this thing in the first place. There's a formula, so just whip out the formula. What does the formula say? The left-hand side is just AB times the product of all the prime divisors, the product over all the prime divisors of AB of this kind of funny expression. On the other hand, if a prime divides a product, part of our Euclid's definition of a prime is that if a prime divides a product, then that prime has to divide one of those two factors. And when I say it divides one of those factors, usually in math, when somebody says that the prime has to divide one of those two factors, they mean at least one of those two factors. On the other hand, because I assumed at the beginning that A and B are coprime, a prime will divide A or B, but not both. And so, when you take the product over all the prime divisors of A times B, what you're going to get will be the product over all the prime divisors of A times the product over all prime divisors of B of exactly the same kind of factor. And now, obviously, if you rearrange the terms in here, if you multiply these parts together, what you will get will be phi of A, and the remaining parts, when multiplied together, will give you phi of B. So, okay, there's a proof. I don't like that proof as well as one that uses the previous theorem about what the Euler Phi function is counting. Let's call this proof number one. Here's proof number two. This is a little more sophisticated. I like this one better. Phi of AB, your left-hand side, that's the cardinality of the set of all congruence classes of modulo A times B that are invertible. Now, how do you get an invertible congruence class modulo A times B? If you have an invertible congruence class modulo AB, that means that, well, it's an integer x with the feature that x times y is congruent to 1 for some other integer y. But of course, if x times y differs from 1 by a multiple of AB, that means that x times y also differs from 1 by a multiple of A and a multiple of B as well. Which is to say that if x is actually in Z mod A times B cross, then take your integer, which is invertible mod AB. When you reduce that same integer modulo A, then guess what? It has an inverse. Namely, its inverse mod A can be exactly the same integer that you used as the inverse modulo A times B. If you have something that's invertible mod 12, it'll also be invertible mod 3, because do you want to know what its inverse is? You just use the same inverse that you used mod 12. So that would be the conclusion here, is that if X is invertible modulo A times B, then X, if you reduce that further modulo A, you'll get something that's invertible mod A as well. In other words, if you take the following function that takes congruence classes modulo A times B and first reduces them modulo A and then modulo B, put those two reductions together with parentheses around them and a comma between them. This is a function then that takes integers in this one set of congruence classes and gives you a pair of congruence classes, one modulo A and one modulo B. We actually discussed this kind of a mapping before when we were talking about the Chinese remainder theorem. So F takes a congruence class modulo AB, and it simply reports the congruence class of the same integer, first modulo A, and then modulo B. Okay, so this is a function that we've discussed before when we were talking about the Chinese remainder theorem. So we've already used the fact that this is a function. So for example, this is the function that took those 12 congruence classes modulo 12, and it gives you various combinations of congruence classes modulo 3 and modulo 4, because 3 and 4 are co-prime. We've already decided that this function is both one-to-one and onto. One-to-one correspondence. Meaning, if you have two integers that have the same reduction mod A and the same reduction mod B, well then they must be congruent to each other modulo A times B. That's what it means to be one-to-one. And the fact that it's onto is the statement that, hey, you can give me any congruence class mod A and any congruence class mod B, and I can find an integer which is congruent to the first requirement mod A and at the same time congruent to the second requirement mod B. So we've done all that kind of thinking before with the Chinese remainder theorem. This observation at the top that I made on the previous page tells us this function f sends the invertible congruence classes modulo AB to invertible congruence classes mod A and invertible congruence classes mod B. So it will take you to the subset of this Cartesian product where the first component comes from this subset and the second component comes from that subset of Z mod B. So if you have a one-to-one correspondence, that means that it pairs off with just one element of the domain with one element of the codomain. And if you also know that it happens to choose these particular elements of the domain and pair them off with these particular elements of the codomain, then the cardinality of this set will be the cardinality of this set. And the cardinality of a Cartesian product is just the number of choices you have for what goes before the comma times the number of choices that comes after the comma. Of course, now if you use what I had a few minutes ago, the cardinality of this set is exactly what we've defined as the Euler Phi function. So what I've just proved for you is that the Euler Phi function of the product is equal to the product of the Euler Phi functions of the two factors. And that's what I wanted to prove. Now I'm going to bet if I took a poll and I asked you which of these two proofs you like better for this theorem, 100% of you would choose proof number 1 instead of proof number 2 because it's only 2 lines and it's easy to understand and it's probably the proof you would have invented on your own. Nonetheless, I got to tell you that to a mathematician, this is such a classy way of thinking about it, and it ties it in with things like the Chinese remainder theorem, and these are actually what we would call homomorphisms between. This is between 2 rings, and this is between 2 groups. So there's a lot to be said for this proof as well. And those of you who intend to go on and take some more high-level math classes, hang on to this proof. And then when you're taking your ring theory class, ask your teacher if this is related to what they're doing in their class. Anyway, it's an important feature. Now, this does use the fact that A and B are co-prime. As it turns out, this is a setting that we see for a lot of functions. I've now defined the Euler Phi function for you as being a function that takes in positive integer and it gives out other positive integers. There are lots of functions that do this. Obviously, you could have, I don't know, the squaring function, or the function that takes a number k and sends it to 2 to the k. Those are a lot of functions that you would have studied in a calculus class. In a calculus class, you didn't care too much that you would get integers out, but then again, you often did if the input was an integer. For a number theorist, functions that go from n to n are of special interest. We do like to talk about functions like that, but out of all of the functions that pair integers to integers, the class that seems to have the most interest are functions that do something nice with respect to, well, addition perhaps, or multiplication, and in particular things that take into account something about primes. Well, those are things that we like better. We like to study primes in number theory. So a theorem that, well, you know that anything that refers to the Euler Phi function is going to have something to do with primes, because that's how I defined the formula for it. The Euler Phi function, though, has this feature, at least for an A and B are co-prime, as do other functions in number theory. So there is a definition that we use for such functions. If you have a function that sends integers, positive integers to positive integers, and it does have this feature that whenever two integers, when you take 2 co-prime inputs, then you automatically get co-prime outputs. No, I didn't say that right. If you start with 2 co-prime inputs, then phi takes the product of those 2 inputs to the product of their outputs. Then we say that this function phi is multiplicative And it turns out the Euler Phi function is just the first of many functions that do this, and there's a lot of interesting applications of functions of that sort. There are some simple ones. One of them is the so-called Möbius function. And like I say, this has something to do with primes. This is a function that's very simple in terms of its values. The outputs are either +1, -1, or 0. And the 0 is an easy one. It's the mu of n is equal to 0 if n is divisible by any square other than 1. Perfect square other than 1. Now I'll pause while I let that sink in. If you think about the prime factorization of a number n, then a number is divisible by some square if and only if it's divisible by the square of a prime, which is to say, if and only if when you write n as a product of primes to different exponents, if any of those exponents is bigger than 1, then you can see a square that divides n. And if all of the exponents are equal to 1, then n would not be divisible by any square. So saying that n is not divisible by any square means that you have only different prime factors, that each of the primes that divides n only shows up to the first power. So numbers that don't give you a 0 here are the numbers that are not divisible by a square, and those are said to be square free. And that happens precisely if all these exponents are equal to 1. Well, 1 or 0. You still sometimes see it in the older literature. It's amazing how some of this stuff just persists for no good reason. Quadrat frei. So for some reason, that's one of those words that you still see in German sometimes, like eigenvalue. Anyway, then the other values are +1 and -1, and they use +1 if k is even and -1 if k is odd. In other words, mu of n is just -1 to the k unless any of the e's is bigger than 1, in which case you define the the Möbius function to be 0. So this is Möbius. And it is another example of a multiplicative function, because if you take mu of a times b, and a and b are co-prime, well, there's a few possibilities. It's going to be, let's see if a and b are co-prime. Well, if a and b, if when you look at the prime factorization of a and b, if you are going to get a 0 because you had a higher exponent, then you know what? I'm just not going to write anything. I'm just going to say it. If a and b are co-prime, the only way that you're going to get a 0 is if you had a prime power that showed up to an exponent higher than 1. Well, that's going to have to mean that a or b separately had a prime power that show up to an exponent greater than 1, because it says here that a and b are not supposed to share any prime factors. So in the case where you get a 0 for a times b, it's because you had a 0 for either mu of a or mu of b. If you don't get a 0 for mu of a times b, that's because the number a times b is just a product of distinct primes. Well, how many primes show up? You list all the primes that were in a, and you list all the primes that were b, and you take the union of those. So the number of prime divisors of a times b is the sum of the number of prime divisors of a and the number of prime divisors of b. Here what I'm using is the fact that this mu function, in the case where you have all distinct prime divisors, it can be written, you can combine these two lines by just saying it's -1 to the k. So that's then going to be the product of -1 to some power for this guy and -1 to the corresponding power for this one. So this is the result that gives you the fact that this is also another example of a multiplicative function. I'll discuss a few other multiplicative functions with you in the days to come. I'm going to retreat a little bit back to the Euler function and give you a cool theorem about that one. Now, I've been talking about multiplying values of the Euler Phi function, but sometimes you want to add. And specifically, I'm going to add values of the Euler Phi function over a range of numbers d that all divide a single number n. If you look at the Euler Phi function of d for all the divisors of n, what you're going to get will be exactly n. So you guys were asking me last time about just how much bigger phi of n is than n. Well, notice that one of the sum n's that's in here is phi of n itself. I mean, n divides n, so phi of n is one of the things you're adding up in here. On the other hand, if n has a lot of divisors, then you're going to have a lot of things to add up in this. So that's going to tend to make phi of n be comparatively small. I mean, because there's so many other terms that have to be added in to the phi of n to get n. So phi of n tends to be much less than n when n has a lot of divisors. That's actually obvious from the other formula that I've given you for phi of n, but it shows up in a different way here. So let me have a proof of this one. I think we can finish that before we run out. All right, well, the proof of this uses the fact that phi of n measures the cardinality of the integers in Z mod n that are invertible. Those are the congruence classes modulo n that have a GCD with n that's exactly equal to 1. Okay, well, if the GCD of n and some congruence class mod n, if it isn't 1, then what is it? Well, what can I say? The GCD of any two integers is, in particular, a divisor of both of those integers. It has to be a divisor of n. So what we can do is to write the set Z mod n as being a union of a bunch of things. We'll start off with Z mod n cross, and then everything else. So again, I'll just rewrite it. These are the congruence classes of A mod n. It's the set of all A mod n such that the GCD, I don't know why I wrote uppercase n here, the GCD of A and n is exactly equal to 1. Well, if the GCD isn't 1, then there's also the congruence classes for which the GCD of A and n is, well, 2, or whatever other divisor you want to write for n. You take a union over all possible divisors of n of all of the congruence classes that happen to have the GCD of A and n equal to whatever that divisor is. Go one divisor at a time and gather together all the congruence classes that have that divisor. I mean, you know that these sets are non-empty, right? I mean, at the very least, if you give me a divisor of n and you say, hey, tell me about the congruence class of D modulo n, well, I would say, gee, I wonder what the GCD of D and n is. If D divides n, that'll just be D itself. So when you draw my attention to any single divisor of n, then I will certainly have at least one element of this subset. So this is a way of partitioning all the elements of Z mod n according to what is the GCD of this congruence class with n itself. Okay, so now the question is, exactly how big is such a congruence class? How many elements are there? The cardinality of the set of all of these congruence classes mod n for which the GCD of A and n is exactly equal to D. Well, I wouldn't be asking that question if I didn't have an answer, so let me show you. Well, let's see. When you tell me that the GCD of these two numbers is D, then in particular D is a divisor of both A and n, which means that A over D is an integer. And of course, and D also has to divide n. So n over D is an integer. And in that case, you know that the GCD of that integer and that integer is exactly the GCD of A and n divided by D, which will be equal to 1. So that means that A mod A divided by D, or at least the congruence class of it, is an invertible element of the congruence classes, of the set of congruence classes of the integers modulo A divided by D. And I know exactly how many elements there are in that set. Namely, it's the Euler Phi function of A over D. Oh, I'm sorry. This should be n over D. That integer is co-prime to this integer, so this is an invertible integer modulo this one. And there are exactly and phi of n over d elements here. So that becomes the cardinality of this set. The number of congruence classes that have a GCD exactly equal to d turns out to be Euler Phi function of n over d. You check it out. Go back to the integers mod 12 and ask how many of those integers mod 12 have a GCD that's exactly 1 or 2 or 3 or 4 or 6 or 12. And in every case, you'll get this Euler Phi function. So if that tells me how big each one of these subsets is, then the cardinality of the set on the left is the sum of the cardinalities of each one of these. The cardinality of this one is n divided by 1, phi of n divided by 1. The cardinality of this set is phi of n divided by d1. Cardinality here is phi of n divided by dk. So it's the sum of phi of n divided by d, where d ranges over all of the divisors of n. That almost, but not quite, finishes the theorem, because I said I would get n as a sum of values of the Euler Phi function, but it was supposed to range over d, not n over d. Yeah, but you know what? Every time you write every time you write n as a product, you're writing it as a product of two things. And so if you let d range over all of the integers, all the divisors of n, and every time you list a divisor of n, let's do 12, for example. Every time you list the divisors of 12, I ask you to worry about the number n over d to compute phi of n over d. Well, now you'll be computing phi of 12, then you'll be computing phi of 6, phi of 4, 3, 2, and 1. But guess what? You just computed phi of d for all the divisors of n. This is the same, if you like, using this notation here, I'm computing phi of e, where now e ranges over all of the divisors of n, and that is just a change in notation from the thing that was to be proved in the first place. So I'll stop there. We have a few other cool things that we'll be able to say about the Euler Phi function, but I'll save those for next time. You guys have any questions, any comments? Let's see, I was scanning the...
What is the use of the Möbius function?
Oh, that's a very good question, and it has an answer that maybe you're not expecting. There is a theorem that says that when you take any function that, if you have any function that you would wish to compute, do a computation of this form, if I compute the, let's say, alpha of d, where d ranges over the set n, that can be used to calculate another function that you could define over any integers. The Möbius function, the Möbius function is used in the Möbius inversion formula to say that you can recover the original values of the function alpha by taking a sum of some values of the function beta. I'm sorry. You sum over the divisors of n, but you need to use the Möbius inversion function in here. So for example, we could compute, let's see, another way to compute the Euler Phi function. Well, I've just proved for you that n is the sum of phi of d, where d ranges over the divisors of n. So put the identity function for the beta and the Euler Phi function for the alpha. Then according to this formula, I can compute Euler Phi function of n by taking a sum of some of the divisors of n with a plus sign, other divisors of n with a minus sign, and some with a 0 as the coefficient. So that's kind of an unexpected formula that you can compute Euler Phi function not by multiplying some things together, but by taking a sum of, well, some of the divisors with a plus sign and some with a minus sign and others not at all. So this is a famous theorem. I wasn't going to get into this, but since you asked, Möbius inversion formula. It lets you invert the relationship between one function alpha and another function beta.
That's really nice. Thank you.
Yeah, I'm glad you asked, actually. I should have mentioned. All right, guys, I went over again. Sorry, but I'll freeze it here. We'll come back next time. I'll put this up on YouTube for you.